Hey, chemistry team. Hello. Welcome to video number 6 in the equilibrium series. What we're going to learn today is how to manipulate equations, because chemists like to manipulate things. We like to take equations and move them backwards and multiply them by 2's and 3's and halves and do all this fun stuff. Eventually, what we're going to be doing is taking, in the next video, known equilibrium equations where we know the K values, and combining them together by manipulating and combining them to get a new overall equation where we don't know the K value. And there's some rules mathematically that allow us to do it. But we need to know what the rules are if we alter an equation, an equilibrium equation. How does that affect the K value? Is the K value dependent on it? Is it independent upon it? Of course it's dependent on it, otherwise we wouldn't be doing this video. So 2 basic things we can do to manipulate an equation, all right? First, if we have some equation, we can multiply it by some factor, and it still maintains the balance. I can take an equation, I can multiply it by 2, I can multiply it by 3, I can divide it by 2, which is the same as multiplying it by 1/2. So let's just call that factor we multiply an equation by little n, all right? And the rules in equilibrium say that if I take an equation and multiply it by some factor, let's say I multiply an equation by 2, right? I have to take the original K value and raise it to that power of that factor. So if I multiply an equation by 2, I'm going to end up squaring that K value. If I multiply it by 3, I'll end up cubing that K value. If I divide it by 2 or multiply it by half, I'm going to take K to the 1/2 power. Now the rules for thermodynamics later are going to be different. We're going to do the same stuff. We're going to be combining equations using Hess's law, but the mathematical rules are different in thermodynamics, but the process is the same. So this is the first rule. So let's just do a quick example. Let's say I find this equation with a known K value, and that could be a Kp or a Kc, doesn't really matter. So if I have 2 moles of NaCl gas, giving us 2 moles of NO gas and 1 mole of chlorine gas, and it has a K value of 9.2 times 10 minus 6, let's say I need to manipulate this by multiplying it by 2. So what I'm going to do is I'm going to take this equation. I like to personally put brackets around it and remind myself what I'm doing. You don't have to do it. A lot of students just do it in their heads, but I tend to forget where I'm going, so I like to have a trail of what I've done to things. If I multiply this by 2, I'm going to get a new equation. So let's write that down. Let's put our new equation here. And I'm going to take that coefficient of a 2 here and multiply it by 2. So I'm going to get 4 moles of NaCl gas. And then I take this 2 times 2. I'm going to get 4 moles of NO gas on the product side. And 2 times 1 gives me 2 moles of chlorine gas on the product side. So there's my new equation, right? I've manipulated it. Now, by changing the equation, I'm going to be changing the K value. So that K value, since I multiplied this by 2, I'm going to raise that K value to the power of 2. I'm going to square it. So my new K value will be the original K value squared, right? So that's going to be 9.2 times 10 to the minus 6 squared, and since this is essentially a multiplication, I'm going to be limited by the 2 sig figs. I get 8.464, good to 2 significant digits, 8.464 times 10 to the minus 11th power. And again, personally, I just like to use that dotted dash line to separate my significant digits from my non-significant digits. Whatever your teacher does at that time, go with it, but try to track the uncertainty. Since this is closer to 8.5 than it is to 8.4, I'm going to be rounding that up to 8.5 times 10 to the minus 11. So I like to draw that little arrow to show the rounding process and put my final rounded value in brackets, because that makes it easier for your teacher to grade on a test. If you don't box your answer on an exam, your teacher's like, "Where's your answer?" And then they're just finding out where your stuff is. So the clearer your work is, the easier it is for us to grade. And if your teacher likes to give partial credit, it makes it easier. So it's an insurance policy for you on exams and quizzes to be as clear as possible and show as many steps as possible. And in my case, tracking uncertainty as well. So this is if we multiply some equation by some factor. Next, I'm going to pause this and we're going to erase this board and put up a new one where we're going to take equations and reverse them. Different sets of rules. We'll be right back. All right, gang, so what we're going to do now is, what if we reverse an equation? That's something we're going to do quite a bit when we're manipulating equations using Hess's law in the near future. So the rules for that mathematically, if we reverse an equation, we inverse the k value, right? Because essentially if we reverse an equation, you're multiplying it by -1. So k to the -1 is 1 over k. So it's kind of like the same original rule, but we're just going to treat it as a separate one, all right? So let's use an example. Let's say we have some hydrocyanic acid here, ionizing in water. Weak acid forming hydronium ion and the cyanide ion. Very low Ka value, 6.2 times 10 minus 10. That's tiny. That's a really weak acid. And again, you can look at this up on your Ka tables. So I'll give you a view of it here. So here's your hydrocyanic acid, right? Where did it go? Hydrocyanic acid right there. You see the HCN and the 6.2 times 10 to minus 10. So again, download these on your phone. From my website if you're in my class, or just look them up in Ka tables. They're all over the place, right? So let's say we need to reverse this equation. So let's do this. I'm going to write a note to myself again. So I'm going to take this equation, and I'm going to remind myself that I am reversing it. So we're not going to now maybe in the future we'll have to multiply by 2 or 3. But for now, let's just say we reverse it. Let's look at the effect on the K value. So let's write my new equation, all right? So let's put the new equation, which I'm just going to write it backwards. So my products become reactants, my reactants become products. So I'm going to have the hydronium ion on the left-hand side now, plus the cyanide ion. And then my reactants become products. So the hydrocyanic acid goes on the product side now, and the water goes on the product side now. So I'm just flipping my equation around. My new K value, right, will be equal to 1 over the original Ka value, the 6.2 times 10 minus 10. So let's take 1 divided by 6.2 times 10 to the minus 10. Get our trusty dusty calculators here and inverse that. 1 divided by 6.2 times 10 to the minus 10th. And I get I get a pretty big number here. Let me put this in exponential notation. Looks like 2 significant digits. I get 1.6. Vertical dash line 1, 2. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th. Good to 2 significant digits. That's closer to 1.6 than 1.7, so I'm not going to round it up. So I keep it as 1.6 times 10 to the 9th power. That is the new K value by reversing that equation. So pretty simple stuff. So in the next video, we're going to apply these principles and do some more complicated Hess's law stuff to find K values for equations that we can't find, but maybe we can manipulate equations we can find K values for, applying these rules and get unknown K values. It's pretty fun stuff. It's like logic problems. Enjoy. We'll see you in the next video.